Hello and welcome to another recording of these lecture series regarding room temperature semiconductors for gamma ray detection and imaging. In this module, I'll present the work of the Orion Research Group, which is underneath Dr. CdZnTe at the University of Michigan. And this is him right here. And we revolve our work around 3D position sensitive pixelated cadmium zinc telluride for gamma ray detection and imaging. We manufacture these detectors, and we also do research revolving around them for better reconstruction techniques. And we also use them for imaging. So we work on image reconstruction techniques and restoration of the gamma ray sources. Why are we interested in wide bandgap semiconductors for gamma ray detection? In the previous module, I showed that there are two other major detectors, gamma ray detectors, available. One of them is scintillators, the other one is gas-based detectors. And the major reason why we want to use these semiconductors is better energy resolution. In this plot, I show the different energy resolutions associated with the scintillators, which is in blue, and the red, which is semiconductor-based. Energy resolution is basically the uncertainty associated with each detection of the gamma ray. This is, let's look at the photo peak. This is the way we measure the uncertainty or the resolution associated with the detector. And it has to do with the full width at half maximum. What we do is we look at the half maximum of the peak. So let's say the peak here has a value of 1. We go down to 0.5 and we look at left and right of the peak, and we see the delta of the energy or the difference in the energy locations. And we call that the measurement uncertainty. And we divide that with the single amplitude. This is resolution, and this is and we use the full width half max to report the resolution of our detector. Sodium iodide is the most popular scintillator out there in the market, and it has around 7%. It's very cheap, and it's used by a lot of different research groups and a lot of different industry practices. The best scintillator out there currently in the market is lanthanum bromide. It has about 3% resolution, maybe slightly better than 3%, but it's still very, very expensive. And they've been working on this for a long, long time to try and increase the resolution of, or improve the resolution of these scintillators, but they have no luck so far. And a lot of money is being poured into it. What we deal with is semiconductor-based. Currently, we are at less than 0.5% with CdZnTe. But because of the statistical physics nature of the detector, we can push it down all the way to around 0.2%, but we have yet to get there. And we will explain why it is quite difficult in the next few slides. Another reason why we are interested in semiconductors is because they tend to have higher Z or higher stopping power. This is a list of the different semiconductors associated or out there. The CdZnTe, cadmium zinc telluride, is the one that we operate right now. It has high Z and high density compared to germanium. Germanium is the gold standard that's currently on the market, but it needs to be cooled with liquid nitrogen. Thallium bromide is a new type of semiconductor which is currently under investigation by our research group and a company over in Boston called RMD. You can see that we're trying to increase the stopping, the Z of the material, as well as the density. Another reason why we want wide bandgap semiconductors, this is wide bandgap instead of just any other semiconductor, is because we don't need cryogenic cooling. The germanium detector, or the high purity germanium detector, which is, again, remind you, the gold standard, which is used by a lot of research groups, needs to be cooled down with liquid nitrogen, right? That is 77 Kelvin, 200 below 0. They have very small wide band gaps, so that very small band gaps. So that means that if you operate at room temperature, the excitations due to thermal reasons elevate it to the conduction band pretty easily, and therefore there's a lot of noise associated with this detector if it operates in room temperature. But if we have a wide bandgap semiconductor, as like CdZnTe, we can actually operate it in room temperature, and this is the basics of our research group. There are several challenges associated with cadmium zinc telluride, and one of them is that there is a lot of hole trapping. I remind you, when a gamma ray deposits some energy in the detector, an electron is ejected by whatever gamma matter interaction means, and a vacancy is left, so there's a hole. In germanium, holes have very good mobility, so they can move very easily. But in CdZnTe, that is not true. Another reason why there's a technical challenge is that these semiconductors are pretty expensive because they have to be extremely purified. The way they're purified is that they basically have a zone refinement. What they do is when they grow the boule out, they have this heater, traveling heater, that try and moves the impurities out by melting it and then letting it reform or self-assemble back again and try to remove those impurities out of the boule. So in regular semiconductors, when a gamma ray deposits some energy and an electron is ejected, the vacant if there is a bias across the detector, because there is some voltage across, the electron and the hole will drift towards the respective electrode. So right here, this is the anode, and the electron will drift towards the anode because it's positively charged, and the hole will drift towards the cathode because it is negatively charged. But in CdZnTe, that is not really true. Holes do not really move. We actually assume that there is an assumption that the hole doesn't move. How does the physics change? And this is what we're trying to see. When a gamma ray deposits some energy, the electron gets ejected. It will drift towards the anode, and it will induce a charge. This is some amplifier, so let's ignore this. And let's have some recorder somehow over in this logic circuitry. When the electron drifts, it induces some charge, right? The way you can see this is that there's a mirror charge moving in the opposite direction. The signal you would see if it drifts from the cathode to the anode is the full signal induced because it moves through the entire electric field. But if the gamma ray were to interact, let's say like in this location, the induced charge will be slightly different. It will be slightly smaller. It's induced charge because the electron only moves a small portion. It will only induce a small portion that is proportional at the depth of interaction. So this means that if you have a planar anode, so this is a full electrode over the entire anode, the signal is depth dependent. The way we fix this in our research group is that we try and make the signal depth independent. And the way we do this is via the pixelation of the anode. So let's say there's a pixelated 11 by 11 array electrodes. So this is each its own electrode, or I would use the word pixel from now on. The interaction physics is slightly different. When a gamma ray interacts and deposits energy in the cathode side, it will drift, but the way the charge is induced is slightly different, right? In the planar configuration, which we still keep on the cathode side, the induced charge is very linear and it's depth dependent. But in reality, when we have the pixelated nature of the anode, the induced charge is actually slightly different and depth independent. That has to deal with the weighting potential or the electric field associated with the pixelated nature of the detector. So anything that happens in the bulk of the detector is really depth independent. And this is shown right here. This is the induced charge over the depth. So this is as it's drifting. If something drifts from the middle, you can see that the discrepancy between the middle and the edge is actually very small. So this is a depth independent signal. We look at the cathode right now. So this is a cathode signal, which has the pin geometry, and this is a depth dependent signal. Let's say you have some cesium source which emits a gamma ray and also a 32 kV X-ray. We don't see a lot of the photopeak because, again, the gamma rays, when they're produced inside the bulk of the detector, they produce a depth dependent signal, which is not very intuitive to reconstruct. The reason we see the X-ray is because these X-rays have very, very low energy. So that means they don't penetrate the detector as much. So they really happen in one location, which is very close to the cathode. and they're basically at the surface of the detector. So they mostly drift through the entire bulk of the detector, inducing the full charge. That's why we see the 32 keV X-ray. But let's look at the anode side. So this is the anode depth independent signal, which I will show in the next slide. And we will reconstruct the signal with the anode and show you the photopeak. And this is what the anode spectra looks like. This is the photopeak. This is a Compton continuum right here. And this is a backscatter peak associated when it backscatters off of the environment and then hits your detector. And these are the two X-rays you constructed. And you can see here that this is a 0.41% energy resolution, so about 2.7 keV. And there are the noise associated. The reason why it's not, what we want is a delta. And the reason why it's not a delta is because of two things. One, it's electronic noise, which actually it's the major noise contribution to this detector. And it's also poor detector performance. You can see that it's not fully uniform throughout the detector. So this is each pixel in the detector. And you can see at some point you have 0.38%, sorry, 0.38%, that's correct. And in some pixels you have 0.55%. That is because there is some non-uniformity in the crystal, as well as non-uniformity in your electric readout. So, right, the way we read out, we have to read out every single pixel. And maybe there's some more noise associated with that pixel than a different pixel. What I showed before was the spectra for one single interaction. So that means only one pixel triggered. Let's say a gamma ray comes in, Compton scatters off one pixel and then deposits energy in another pixel. So you trigger two pixels. The noise increases because you add the noise from these two readouts. So when you read multiple pixel events, the noise slightly increases, right, to 0.58%. This is the Polaris system, which is the old analog system. And there is 18 crystals in there. So there's 2 arrays of 9. And there is over half a kilogram worth of CdZnTe. Each one is 2 by 2 by 1.5 centimeters cubed. So it's 6 centimeters cubed. It's about yay big, just to show you for an idea. And we can get better than 1% fourth half max resolution at 6:2. Also, over the development of about 10 years, we are able to do real-time gamma ray imaging. We'll show this in the next module, how gamma ray imaging works. This is the physical system. So you can see that these are the each individual crystal. On the anode side, I remind you that there is a pixelated array, and we put the anode side in the middle of the two. So this is the two arrays. We put the anode side in the middle. One, to ease the burden of reading out the electronics, and two, because we want the cathode to face out. Because when the gamma rays hit the cathode, and if they're very low energy, you want them to occur at the cathode side. If you have readout electronics, they are disturbing with the readout process, and they attenuate some of the gamma rays coming in. And this is how the package looks like. The crystals are in here. These are all the electronics associated with reading out these detector arrays. So with this system, we have achieved very high resolution. So this is in the red, the CdZnTe detector, compared with the sodium iodide detector. I remind you, sodium iodide is a scintillator-based detector. But when we compare it to an HPGE, high purity germanium detector, which is cooled via liquid nitrogen, you can see that I'm not quite there yet. There are some peaks that are very easily distinguishable in the high purity germanium, but not distinguishable in the CdZnTe. The way the technology works also minimizes the impurities associated with the crystal, the CdZnTe crystal. Because it's pixelated, we can do a gain correction based on each pixel to see which one is performing poorly. So therefore, we can increase the capabilities and the resolution of the detector. Finally, using the system, we can do real-time gamma ray imaging. So this is a gamma ray image. One thing I didn't talk about is that we are a 4-pi imager. 4-pi is of units of solid angle. Basically, what this means is that we can image 360 around the detector, and also 180 and down. So that's a full sphere. We can image a full sphere around us. And because we have this great energy resolution, we can also tell the color of the gamma rays being emitted. So right here we see several students holding the gamma ray sources, and the color is associated with the different energies of the sources. So this could be cesium, this is sodium, this is maybe cobalt or other sources that are in the image space. But we have full 4-pi image sensitivity. Because we have such a sensitive detector and such a 3D position sensing detector that gives us a lot of information, we actually know what interactions are happening within the detector. We can know the photoelectric absorption because we don't see that there's a scatter. We come in here, it's photoelectric absorption. Or we can see a cut and scatter when we see multiple scatters originating from the same gamma ray. We can also tell if it's pair production by tagging the 511 coming out of the pair production site. We can also see a muon. When a muon comes, they have extremely high energy and they cause these particle tracks or these high energy tracks within the detector system. We also have a neutron signal coming out, and we'll talk about that in the future slides, but it will now remain as a question. But what we cannot do, unfortunately, is an event-by-event tagging of what a neutron event is, unlike organic scintillators that use pulse shape discrimination to distinguish between a neutron and a gamma ray. Currently, the research of interest is to upgrade the analog system, which I showed before, and we call the Polaris system, to the digital system. And we have reduced the noise in it significantly and allowed for more advanced processing of the detector. So we are now less than 0.5% with sub-pixel resolution. I'll talk about where the sub-pixel resolution comes from and what it is. In the analog system, we had the CdZnTe detector. The signal will then be amplified by some circuitry and then read out by some analog logic. The analog logic will shape the pulse and then detect the peak, right? There is the induced charge. We look at the peak of the pulse. And again, the peak, the amplitude of the pulse is associated with the energy deposited in the detector. And we also have some other circuitry that measures the timing of the trigger and all kinds of things like that. So we get the energy and depth resolution. That's the only thing we get out. What we did as a research group is replace this electronics logic with a digital electronics logic. So when the signal comes out, it gets collected on a buffer. The buffer is a bank of capacitors that basically measures like ones and zeros, the amount of charge in each cell. And then we have some trigger mechanism that if there is some amount of energy deposited, it will then be read out by some computer. So this is a ADC, analog to digital converter, and then it puts it into some digital format that we can read out later for later processing. Here we can see the different pulses, the digitized pulses coming out. The red is the triggered pixel, while the neighboring green and purple are the neighbor pixels. So let's say we trigger the center one and we read out the neighboring signals, and we'll talk about why we do that in a later slide. We also read out the cathode because the cathode gives us a depth-independent, a depth-dependent signal. Again, the anode is a depth-independent signal, while the cathode is a depth-dependent signal. If we take the ratios of the two, we can actually infer the depth of interaction. But anyway, this is what it looks like. The signals are coming out, and we can process it and result in a high energy resolution. One thing we can also do is read out the neighboring pixels as I show here. So this is a triggered pixel, and then the neighboring pixels are the neighboring 8 pixels. And the way the detector works, because of the physics associated with it, is that when you look at the neighboring pixel, if the interaction happened closer to the left pixel, say, the induced charge will look slightly different on the left side than that of the right side. I will show this right here. So this is the subpixel estimation associated with each event. And you can see that the neighboring pixels induce a charge. There's a induced charge on the neighboring pixels associated with the subpixel location of the detector. Let me stop at 1. So this is, you can see that it's closer to the bottom pixel than top pixel. So if you look at the neighboring pixel of the bottom one, you can see that there is a larger peak with the bottom one than the top one. This implies that the interaction may have happened closer to the bottom pixel than the top pixel. So we put it slightly below the center of the pixel. Again, we look at the left and right. You can see that the induced charge on the left side is slightly higher than that on the right side. That means it may have happened closer to the left side. This uncertainty is about 250 microns, which is about the size of the electron cloud. When I say electron cloud is because when the electron is produced from the gamma matter interaction, the electron still has energy and it's moving around. It's moving around and creating electron hole pairs, but it still has some extent in size, and that reduces your position certainty and increases your uncertainty. The way we get neutrons, or we try to infer that there are neutrons, is via the neutron effect, the neutron matter interaction effect. Neutrons behave slightly different than gamma rays. In this scenario, the neutron, which has very low energy, gets captured on the cadmium. The cadmium is then excited and then releases a gamma ray, a characteristic gamma ray associated with what the neutron has captured on. For cadmium, the characteristic gamma ray that we look for is 558 keV. So 558 keV gamma ray gets emitted. If we detect that 558 gamma ray, we can infer that there is a neutron source present. Let's look at 2 spectra of plutonium. This spectra is from CdZnTe, and the bottom one is from germanium. You can see that there is one peak that's not visible in the germanium detector. That's because the gamma ray captures on the cadmium, and there is no neutron-sensitive detector, a neutron-sensitive element in the germanium. Germanium is not neutron-sensitive. So we can infer that there is a neutron source here, while the HPGE will not tell us anything, that there's neutron present. However, we're still trying to improve our energy resolution to be competitive with HPGE. Why are we interested to push the resolution to lower uncertainty? And the way we can look at it is for homeland security aspects. The way people do grading on like plutonium samples is by looking at 2 gamma rays emitted by plutonium-240 and plutonium-239. So these are the 2 cameras, 642 and 645. You can see that they are very close in energy and not very far apart. They're about 3 keV off. And these are the 2 peaks that are being used to grade this plutonium, because we look at the ratios of the 2. Over here, you can see that this is associated with one type of, so the dotted line is associated with one type of enrichment, and the solid line is from another type of enrichment. This is the 645 from plutonium-239, and this is the 240 from plutonium-642. And you can see that they're very distinguishable using germanium. And they take the ratios of the 2 to try to infer the enrichment of the plutonium samples. We try to do the same with our CdZnTe detector. And we take the ratios of the 2 and we can try to infer that there's 3.6% plutonium-240. In reality, it's actually 5%, but we are within 2 sigma of the true enrichment. With the new digital system, we have now pushed it to world record performance. This is a spectra associated with the best CdZnTe crystal, about 0.31% full width half max at 662. You can see that some pixels do even better. They're down to 0.28. I don't see a better one. But anyway, this is an extremely high performing detector, and we're really getting close to that of germanium. This is very competitive with mechanically cooled germanium. There are 2 types of germanium detectors. One is mechanically cooled. The other one is liquid nitrogen. The mechanically cooled uses some kind of pump to reduce the temperatures. This is called Joule-Thomson throttling. So PV equals nRT, you reduce the pressure, you reduce the temperature. but those systems are extremely noisy, and we're getting very competitive with those mechanically cooled detectors, but we still have to reach down to liquid nitrogen performing levels. The slide before was for only one pixel event. If we add the pixels together, meaning that there's multiple interactions, I'll remind you that the noise is slightly higher because you read 2 channels out. The resolution slightly decreases to about 0.5%, but this is still extremely high performing. This is all done in room temperature, I'll remind you again. We compared this system with several other systems available. The sodium iodide with 7% resolution is quite poor. You can see that you can barely see any features, and it's just one big hump. Lanthanum bromide, which has about 3% resolution, you can see that we can distinguish between these gamma rays and that gamma rays, but we can't see any more features. When we look at the digital system, so this is Orion Alpha, the digital system that we currently have in operation in our research group, you can see that we can very well distinguish several peaks, but we're not there yet compared to what's offered by high purity germanium. This is right here. Now, if you are, so Dr. He has been working on this research for over 20 years. And a few years ago, he created his own company called H3D, which is a spin-off company over the University of Michigan. The way you spin up a company is that the university owns a lot of the patents and they license it out to a private company. This is H3D. And these are all the former students of Dr. He that have gone eventually into the company to try and produce this product. So this is what they sell right now in the market. They're starting newer models, which I'll show right here. This is the H420, and it can do gamma ray imaging. And this is an image of a nuclear facility and look at cobalt and some facility. But what they can also see is the cesium on the floor that has been spilt, because we get full 4-pi imaging capabilities. We can see where the gamma rays are coming from in all directions. So this is a very powerful tool. Another one that they're trying to, a product that they have is the radioisotopic identification. This is given to a user where they can walk around and try and look for the radiation source based on the count rate. And it also gives you some directionality based on the arrows. But this is more designed for like border patrol. If there's a car coming in and you want to see if there's any nuclear material associated with it, this is the detector that you would use. Another interesting work that they're doing is they're mounting this now on the Stryker vehicle, armored vehicle. The idea behind mounting it is, let's say that there is some event that happens, some radiation dispersion device or nuclear weapon goes off. They deploy these Stryker vehicles to try and look for where their event has happened and try and localize it and, well, deal with the matter at hand. And so this is what it's called the Merlin project. And this is now the future of what is now planned for this system, is that this is a single detector. And I showed you that we have now 9 crystals, but what we try to do is expand it to larger and larger arrays. And the idea is if you have a larger array, you have more sensitivity associated with the detector system. You make these huge arrays and you build them into any configuration that you want to maximize the efficiency of the detector. Another project in the conception of this system is to have a network of detectors. If you place them in a lot of different locations, you have this entire system that detects the gamma. So if a source is here, these can triangulate actually the source location. And also the idea is also to give them by the singular soldier to walk around, and you have a network of these soldiers. You can easily localize the different sources out in the field. So this concludes this module, and see you next time.